In this video, we're going to talk about indefinite integrals. So just as a reminder about what we talked about last time. And so the fundamental theorem of calculus tells us that the derivative of the integral from a to x of f of t dt is equal to f of x, and the integral from a to b of f of x dx equals capital F of b minus capital F of a, where the derivative of capital F is lowercase f. Or in other words, capital F is any antiderivative of little f. And this is where the idea of an indefinite integral comes from. And so indefinite integrals are basically something we've already talked about, just with a different name. And so we define the indefinite integral which we write as integral of f of x dx. Notice we don't have any bounds on it. And this is equal to capital F, where capital F prime of x equals little f of x. In other words, the indefinite integral and the antiderivative are the same thing. Just note, the indefinite integral of a function is the most general antiderivative of that function. Okay, so an indefinite integral is literally just an antiderivative. A few more notes to be aware of. We've basically just introduced notation for the antiderivative is all. So we're just going to write it as an integral without bounds on it. And so note, an indefinite integral always includes a plus c at the end. So for an indefinite integral, you'll always include the constant at the end, as it is the most general antiderivative. So you have to include the constant because we can shift by constants, as you might remember from our antiderivative lesson. And the next thing is just a comparison to be aware of. An indefinite integral the integral from f of x dx is a function. Or rather, it's more like a family of functions because of the plus c. That's kind of a technicality. A definite integral, so where we have the bounds from a to b of f of x, is a number. Okay, so this is just an important thing to note between these two. If we have bounds, we have a definite integral, in which case there is a number that we get out. If we have an indefinite integral, meaning we don't have bounds, then we have a function and we have to remember the plus c at the end. And so this is just an important difference to make between the two. The rest of this video is just going to be examples of computing definite and indefinite integrals, just to reinforce this point of what this notation actually means. As we've already done antiderivatives before, this is pretty similar to something we've done before, but now that we have this new notation, it just feels like doing some practice would be good. And so we want to take the indefinite integral of 10x to the fourth minus 2 secant squared of x. Okay, so we want to compute this indefinite integral. And so the way we do this is we're going to split it up over subtraction. So this is the integral of 10x to the fourth dx minus the integral of 2 secant squared of x dx, which equals 10 times the integral of x to the fourth dx minus 2 times the integral of secant squared of x dx. Now, if you do not remember your antiderivatives for things, going back to that video might be helpful, as going forward, the rest of the lessons are going to use antiderivatives quite a bit. And so it's important to remember those. So we've got 10 times, we want the indefinite integral of x to the fourth. Well, using the power rule, that's x to the fifth over 5. Plus, and technically we'd have a constant here. Now we're going to note at the end of this that you really don't need to put the plus constant every time, but I will just to make a point here. Minus 2 times, now we want the antiderivative of secant squared. That's tangent of x, plus some other constant, which I'll call c2. And so we combine things, so we're going to have 2x to the fifth plus 10c1 minus 2 tangent of x minus 2c2, which equals 10x to the fifth minus 2 tangent of x plus 10c1 minus 2c2. But now the thing to note here is c1 and c2 are just arbitrary constants. And so I take 10 times some arbitrary constant minus 2 times some other arbitrary constant. The result is just some other arbitrary constant. As c1 and c2 can be any number, I can get any number out of this combination. So we just are going to write that as c. So we have that the integral of 10x to the fourth minus 2 secant squared of x is equal to 2x to the fifth minus 2 tangent of x plus c, where c is any constant. And so the point I'm making here with the c1 and c2 is that we can just find the antiderivative ignoring the constant and then just stick it on at the end. So when we break things up like this, the constants can still be arbitrary, and so we don't have to follow it through all the way. We just can stick the constant on at the end, which we're going to do going forward. Okay, next, we want to evaluate the integral of sine of theta divided by cosine squared of theta, d theta. So we want to compute this indefinite integral. Well, for this indefinite integral, we don't immediately know the antiderivative. We don't immediately know the answer. So what we're going to do is we're going to rewrite this slightly and use trig identities to come up with what is happening. And so we've got sine of theta divided by cosine squared of theta, which is the integral of sine of theta divided by cosine of theta times 1 over cosine of theta. Okay, so now using what we know, our properties here, we have sine of theta divided by cosine of theta, but that's just tangent, so we're going to have tangent of theta. And then 1 over secant is just, 1 over cosine is secant, so we just get times secant. So now we want the antiderivative of tangent of theta times secant of theta. But we know that that is the antiderivative of secant, and so we get secant of theta plus a constant. And so the indefinite integral of sine of theta divided by cosine squared of theta is just secant of theta plus c. Okay? And so that is what we have found for that example. Next, we want to compute the integral from 0 to 3 of 2x cubed minus 6x plus 1. Now notice this is a definite integral, and so our final answer should be a number rather than a function, because we have bounds. But using the fundamental theorem of calculus, it's going to feel very similar to start with to what we did before. And so the way we start this is we're going to find an indefinite integral and then plug in the bounds. So that's what the fundamental theorem of calculus part 2 tells us, is you find any antiderivative, or in other words, find the indefinite integral, then plug in the bounds. So for 2x cubed, we're going to have 2x to the fourth over 4, minus 6x squared over 2 plus x. And remember, we don't need to include the constant at the end. We talked about that last time, that if we have a constant, it'll just be killed off when we plug in bounds. And we're going from 0 to 3. And so, just to make it clear, this piece right here, before we plug in the bounds, that is just the indefinite integral of 2x to the cubed minus 6x plus 1, using the power rule repeatedly, other than we didn't include the plus c. And if you include the plus c, it'll just die when you plug the bounds in anyway, because you'll have a plus c minus the plus c, and so they cancel out. And so now we need to plug in our bounds. And so plugging in our bounds, we have 2, 3 to the fourth, over 4 minus 3 times 3 squared, plus 3. I guess I can simplify that slightly. So this piece right here becomes just x to the fourth over 2, and this piece right here becomes 3x squared. And so that's what we're plugging into. And then minus, when we plug in 0, we're going to have 0 to the fourth over 2 minus 3 times 0 squared plus 0. And so this then becomes 81 over 2 minus 27 plus 3, which equals 81 over 2 minus 54 over 2 plus 6 over 2, which is going to be 33 over 2. And so we get out 33 over 2 from this definite integral. And again, notice that we got a number here. Okay, and that's what we'd expect to get because we're doing a definite integral rather than an indefinite integral. Okay, next, we want to find the integral from 0 to 2 with 3x squared plus x minus 1 over x squared plus 1. So again, this is a definite integral, and so we expect to get a number out of this when everything is all said and done. And so we're going to look at the integral from 0 to 2 of 3x squared plus x minus 1 over x squared plus 1. So now what we're going to do is, I did this in the previous one, I just didn't write it down, but we do split it apart into pieces. So we're going to have 3x squared dx plus the integral from 0 to 2 of x dx plus, or minus I guess, minus the integral from 0 to 2 of 1 over x squared plus 1 dx. And we're doing each of these pieces, but then we recombined it, is what we did above. And I'm going to actually do that out in the steps here, just so you can see it. And so here we need the antiderivative of 3x squared. Well, a derivative of 3x squared, the derivative of x cubed is 3x squared. So we're going to get x cubed from 0 to 2, plus an antiderivative of x, that's x squared over 2, from 0 to 2, minus, now this is the one that you may not remember, but an antiderivative of 1 over x squared plus 1 is arctangent. Okay, so that's an important one to remember. So we get arctangent of x from 0 to 2. Okay, so that is the antiderivative of 1 over x squared plus 1. That is an important one to remember, and it's easy to forget. But we can think of this, since this is all just saying plug in 2 and 0. We really are doing x cubed plus x squared over 2 minus arctangent of x going from 0 to 2. And so that's what I said about recombining it. And that's what we did up here. I just didn't even bother to do that step. I just did each antiderivative separately. And you can do it either way. You can either split it up, do each indefinite integral or antiderivative separately, and then recombine them to plug stuff in. Or you can just plug stuff in at this level, although that gets a little annoying because you're just kind of rearranging things in a sense. And so now we need to plug in 2 and 0. So plugging in 2, we have 2 cubed plus 2 squared over 2 minus arctangent of 2 minus, we're going to have 0 cubed plus 0 squared over 2 minus arctangent of 0. So we get 8 plus 2 minus arctangent of 2 minus 0 plus 0. And then arctangent of 0 is 0, so we get 0 there. So we end up with 10 minus arctangent of 2. If you're curious, this is about 8.89. And so, like I said before, though, we got a number out. So this definite integral gives us a number when we compute it. And one thing to be aware of is just remember what this number represents. So we had our formula here that we were looking at. I'll write it down again. So we were computing the integral from 0 to 2, 3x squared plus x minus 1 over x squared plus 1. That's what we were computing. Well, this number we just computed, 10 minus arctangent of 2, this value of 10 minus arctangent of 2 is the area, the net area, I should say, under the curve f of x equals 3x squared plus x minus 1 over x squared plus 1 from x equals 0 to x equals 2. So remember, that means we're treating area above the x-axis as positive, area below the x-axis as negative. That integral is telling us the net area. So it's giving us that net area in this situation. And then one more example. We want to take the indefinite integral of 2t squared plus t squared square root of t minus 1 divided by t squared. Okay, so once again, if we want to find this indefinite integral, what we need to do is we're first going to break it apart into pieces we know the antiderivatives or indefinite integrals of. And so for the first one, we have 2t squared. I'll actually just split it up over addition, because that's what we're doing. So we're just splitting up each piece over addition. We can do this because we kept the same denominator on each piece. And so this then becomes, we're going to have 2 plus the square root of 2 minus t to the negative 2. And so now we need to take the antiderivative or find the indefinite integral of each of these pieces. And the indefinite integral of 2 is going to be 2t plus, we have the square root of t, which again, this is t to the 1/2. So using the power rule, we're going to have t to the 3/2 divided by 3/2 minus t to the negative 1 divided by negative 1 plus a constant. So we're left with 2t plus 2/3 t to the 3/2 plus 1 over t plus a constant. And so this then is our indefinite integral. And again, since we didn't have bounds, what that then means is that we just get this out. We get a function out. But if we did have bounds, say we wanted to look at the integral from 1 to 9 of this function, so the same function from 1 to 9, then what we could do is we can immediately plug in what we just found. So we can just plug 9 and 1 into what we just found. And so we'd have 2t plus 2/3 t to the 3/2 plus 1 over t from 1 to 9. And that is an indefinite integral. That's an antiderivative, so we just have to plug in our bounds now. And so this becomes 2 times 9 plus 2/3 9 to the 3/2 plus 1 over 9 minus 2 times 1 plus 2/3 1 to the 3/2 plus 1 over 1. And so we get 18 plus, if you do the math, 18 plus 1/9 minus 2 plus 2/3 plus 1. And so this then simplifies to 32 and 4/9. And so that would be the definite integral from 1 to 9. And so doing the indefinite integral is like a step on the road to the definite integral, as we see here.